Show that if some function f is not equal to 0 everywhere, f cannot be both odd and even. Hello, welcome back to the Quant Plus YouTube channel. The question posed at the introduction of this video is a prime candidate for proof by contradiction. I am introducing this as part of the linear algebra playlist on this channel because the examples I will be discussing in this video are related to linear algebra or come from linear algebra. But much like the video on proof by induction, this is a technique that is introduced in any number of introduction to proofs classes and is applicable widely in mathematics and in related fields. So the idea with proof by contradiction is this. You look at the statement that you'd like to prove. The first step is to negate the statement. The second step is to proceed with the proof in a mathematically rigorous way until you reach a point that either contradicts your starting assumption or is fundamentally untrue. And by being fundamentally untrue, I'm thinking about things like if this negated statement indeed held, you'd have something like 0 equals 1, which is never the case. And then the third and final step is to conclude that the validity of the original statement. And as a reminder, we define odd functions as if you were to plug in a negative value for your variable, whether it be x, t, or any other variable, you would get negative f of t. If a function is even, then f of negative t in this example, you get back to your original function. So tying it back to our particular example, the first step would be to negate our statement. And the negated statement would be, there exists some function f that doesn't equal to 0 everywhere, such that f is both odd and even. 2, we're going to proceed with the proof as if this negated statement was true. So, by definition, if f is odd, then f of negative t equals negative f of t. If f is even, then f of negative t is equal to f of t. Because f of negative t equals f of negative t always, we can say we get negative f of t equals f of t, right? Because f of negative t will always equal f of negative t. But because of the definition of an odd function, f of negative t is equal to negative f of t. And by the definition of an even function, f of negative t is equal to f of t. Then, by adding f of t to both sides, we get that 0 equals 2f of t, and 0 equals f of t. F of t equals 0 contradicts our assumption that f of t doesn't equal 0. And so step 3 is we can conclude that if f of t doesn't equal 0, it cannot be both odd and even. Now, the idea of proof by contradiction is great, but many students, when they are first introduced to proofs, myself included, become overly reliant on the idea of proof by contradiction. And in general, if there is a direct proof to what you want to show, it is usually simpler and shorter than a proof by contradiction. So to give you an example of that, let's consider the linear independence of multiple vectors. So kind of to summarize the idea of linear independence, if you have some vectors v1 to vn, those vectors v1 to vn are linearly independent if you consider the linear combination c1 times v1 plus c2 times v2 all the way to cn plus vn is equal to 0. And the only way that you can get that to work is c1 equals c2 up until cn equals 0. And in the case of two vectors, you can think about it as, is one vector a scalar multiple of the other vector? Okay, so with this in mind, let's consider the following example. Show that the vectors 1, 0 and 0, 1 are linearly independent. The direct proof of this is rather straightforward, so let's start with the direct proof. And the direct proof is, let's start off with the vector 1, 0 is equal to some scalar multiple k times 0, 1. But k times 0, 1, scalar multiplication is done component-wise, so you can rewrite this as 0 is equal to 0 in the first component and just k in the second component. And if we consider the equality of this relationship, well, then we can, again, consider things component-wise. So here, by looking at our first component, we get 1 is equal to 0, which is impossible. And in the second component, we get 0 is equal to k, but 0 is equal to k is less relevant. And because it's apparent that 1 is never equal to 0, this is impossible, we can conclude that 1, 0 and 0, 1 are linearly independent. Now, you could also show this by saying that the first component of the vector 1, 0 is 1, and the second component the first component of the second vector, 0, 1, is 0. And so there's no way that if you have only two vectors, you can come up with a linear combination such that you go from a 0 in the first component to a 1 in the first component. And that would be another way to show that these two vectors are linearly independent. Now, it turns out that the direct proof I gave here is actually pretty much that of the proof by contradiction, but still the proof by contradiction is just much more cumbersome. So let's consider the proof by contradiction here. So step 1, we assume that K exists such that 1, 0, the vector 1, 0 is equal to K times the vector 0, 1. 2, as we did previously, we'll say that K times the vector 0, 1 can be expressed as 0 times 0 in the first component and K in the second component. And by our starting assumption, we're going to set this equal to the vector 1, 0. But then again, because we compare things component-wise when we're working with vectors, we get that 0 is equal to 1, which is again impossible. And therefore conclude that indeed these two vectors are linearly independent. So I know I did not necessarily write out a significantly different proof, but consider the alternative way of proving this directly. And that would be that you can write out C1 times vector 1, 0 is equal, or not equal to, but plus C2 times 0, 1 is equal to 0. And by distributing your scalar multiples and adding your two vectors, you end up with the vector C1, C2 is equal to the 0 vector. And the only solution that exists here is C1 equals C2 equals 0. And by definition, that is showing that the two vectors are linearly independent. So that's to demonstrate that in general, if there is a direct proof of something and there's a proof by contradiction, in the majority of cases, the direct proof is more direct by definition, but it's also shorter and simpler. So before we end the video today, I wanted to thank you for the support on the channel. And if you found this content informative, please support the channel. You can do that by liking this video, subscribing, and sharing it with your friends and family. And if you're interested in one-on-one tutoring sessions, please follow the link in the description below. Have a great day.